Welcome to ICDD's InSession Webinars. Steffen Weber, Materials Data Senior Software Programmer, will present SAED PDF Extension. Please remember to visit icdd.com for information on future free webinars, educational events, product information, and to purchase PDF databases and JADE software.
Today's topic of the InSession webinar is the SAED extension in the PDF 4 Plus and PDF 5 Plus databases. Oops, next slide. Okay, so today's topics is mainly we will talk about a GUI overview for the graphical user interface of the SAED extension. We will also talk about some other stuff first, but basically what I want to demonstrate today is how we perform SAED simulations for single or multiple phases in the SAED extension, how the stereographic projection is presented, structure display, image display, and manipulation, how the measurement tools work, like the Scalebar, ruler, protractor, and grid, how to perform a grid indexing on an image, and how to perform a PDF search, either on the PDF 4 or PDF 5 Plus databases. When we speak of the PDF, we mean, of course, our own database, the powder diffraction file, not to be confused with the pair distribution function or portable document format. SAED, selected area electron diffraction, EBSD, electron backscatter diffraction. K-patterns is a generic term for either Kikuchi line patterns that use electron wavelengths or causal patterns that use X-ray wavelengths. BFDH is the Bravais-Friedel-Donnet-Harker crystal morphology prediction. In our software, we have two types of external modules. We have the extensions or PDF extensions. Those are external modules that are bundled with our PDF database. And sometimes in our webinars, we speak of toolkit items or MDI toolkit items. Those are external modules that are bundled with our XRD analysis software, MDI JADE. Both the extensions and the toolkit items are derived from or embedded in a program called MDI TAOS, which is why several of the simulations look identical between the extensions and the toolkit items, and also the structure viewer is identical in both cases. So what PDF extensions are available in our database? We introduced the SAED extension in PDF 4 Plus in 2022, so 2 years ago. Then a year later, in 2023, we added the EBSD extension and the bond histogram extension. And this year, we are adding the BFDH extension in the PDF 5 Plus database. The extensions all reside in bundled EXEs that are located in the database folder. And they can also be executed by themselves if you have created some project files, SAED project files or EBSD project files, and you just want to reload them. Then you wouldn't need to start the extension from the database. You could be running those directly from the folder. But usually we launch the extension from the database user interface from a PDF card window. By using the highlighted drop-down selectors here in this image. And just as a side note, the development of these extensions is strongly affected by user feedback. So far, we had not much or no user feedback. So if you want to see some features included in the future, please contact us with sample files, sample images, and a wish list of features that you would like to see. So first, before we go to the SAED extension and the live demos, we will demonstrate how all extensions are being launched. So I will show an example for each of these extensions and how they are launched from the database. So here in the database, we have Of course, our search that we usually apply to find suitable PDF cards. Let's use the silicon. So when we have a PDF card, then we have these buttons enabled: 3D structure, bonds, SAED, EBSD. When you click those buttons directly, you will go, of course, to the JMOL structure renderer, or to the bond distance information for this card, or to an EBSD simulation for this card, and the SAED simulation. So these are the internal simulation modules, right? So now, in order to launch the extensions, we use these drop-down selectors. So let's take a look at the BFDH extension for this phase, which is quartz, silicon oxide. So in the BFDH extension, we have the default growth rate method, which is defined as 1/d spacing. So, and we would obtain a crystal shape such as this. If we were to disable the Donner-Harker part, which relates to the symmetry elements that have to be applied, if we just use a normal HKL loop and would just use the Bravais-Friedel criterion, we would get a shape like so. But especially glide planes and screw axes affect the shape. So the full Bravais-Friedel Donner-Harker model would look like this. We have multiple drawing options: solid, translucent, for which we can change the transparency, or drawing mode, and so on. We have other growth rate models related to supersaturation. So here, for example, we can look at the growth rate plots and modify the K parameter. So usually in the default growth rate, the large despacing HKLs, which the large despacing usually relates to low HKL indices, and these phases grow slower, and hence they are the remaining phases in the end. Using these supersaturation models, one can reverse that and get some phases in there that should disappear in the standard model. Now, in addition to these standard BFDH model, we also can simulate a powder pattern. We know what the intensities are. Here, for example, there are two reflections with the same d-spacing, but different intensities. So we could say, okay, let's apply XRD multipliers and see how that affects the crystal shape. So here we would get a more realistic looking quartz crystal. And when we look at the HKL table here and show also the d-spacings, we can see that this lower set has different calculated central distances. Let's assign a different color so we can see that better. So these are all phases with the same d-spacing, but different intensity in the XRD pattern. And we can then also change the central distance of those phases in order to adjust the crystal shape model. We also have the option to do a simple overlay. Now, this is not a true 3D scene of this. It's just that we use a trick. We draw the structure first, and then we draw the crystal shape drawing on top. So we can export the crystal shape as images, or VRML, or faceless and polyhedron, or animated GIFs, and so on. So much for the BFDH extension. Let's look at an example for the bonds histogram extension. This launches a new window, and it starts up with the structure from the PDF card that we have just looked at, and the elements in the formula there are pre-selected in the periodic table. They are enabled. One can enable all elements in the periodic table, or just the ones that are present in the formula. Now here at the moment, we look at an aluminum bond histogram. Let's select aluminum oxygen bond histogram. So we have the histogram itself, which can be either showing only a histogram of the minimum values that were found in the structures, or the average, or both. So here the pink histogram is for the average distance values in structures, and the blue ones are the found minimum values. So here for this particular case, we have a bimodal distribution for aluminum and oxygen, and the lower despacing, or the lower distance value, relates mostly to the presence of tetrahedra in these structures. And the larger distance relates more to the presence of octahedra. So whenever we select a distance in the histogram, the table is searched for the first entry that has that distance value, and an example structure is being shown. And one can go through, find other candidates with that structure. One can switch the user interface to a matrix display for 92 elements. And one can click any point here to select a pair, or use the radius sum coloring. The list on the left side also shows the found coordinations. Now these coordination numbers, 1 to 8, are not necessarily coordination polyhedra. This is just the number of nearest neighbors found. And but it can be useful to screen. So here, for example, for the aluminum oxygen, if we look again at the lower distance, we can see that many of them have the number 4 in here related to tetrahedra, and the larger distance list has the number 6 included relating to octahedra. So this was an example for the bond histogram extension. Let's take a look at an example for the EBSD extension. So the EBSD extension, we see the EBSD, the Kikuchi line plot. So here, this extension is very similar to the SAED extension, but it has this option of showing the K patterns, either the Kikuchi line patterns, here for simple body-centered iron, or we can also switch to a causal pattern. When we zoom out far enough, the projection switches to a stereographic projection that is meant to let you identify regions of interest more easily. We could switch to a black on white or other options. You can go to a dark theme, maybe with a black background. So we have different orientation options here. We specify what orientations vector we want to use, UVW or HKL. We use the stereographic projection to find a region of interest. You can also use key shortcuts A, B, C, D for different orientations. And when we have a region of interest, we can zoom out to see the mnemonic projection for this pattern. The structure itself is shown, and the HKL list can show either only the visible HKL or the full HKL list. The WolfNet can show the poles. You can click at poles to get information about them, and also to reorient a sample. Use a click pole as an orientation vector, for example. You can also assign traces. The WolfNet has two context menus, inside the circle and outside the circle. We can, for example, say show only the traces. Let's make the dot small. And now if you, for example, compare the Kikuchi line pattern, the stereographic projection with an actual WolfNet, you can see now this is very similar, right? You can also disable the dial and the net. Now we would have a representation like so. In addition to these renderings in the structural display, we have some settings for the camera, for the simulation options, and for visibility of the pattern. And one can also see a WolfNet monitor here on the right side if one wants to see the structure, the K pattern, and the stereogram all at the same time. And so much for the EBSD extension. And of course, we would have the SAED extension, which we will talk about much more later on, but which would be launched in the same way here. Let's make the radii proportional to f square and the color proportional to f square. And the structural display is synchronized with the reciprocal space plot display. Okay, so these were just some quick demos for how to launch extensions. Let's go back to our slides. So what SAED software is available? We have commercial software. Some of the most more well-known ones are MacTempus, Gatan's digital micrograph, Crystal Maker with its single crystal module, and many others. And then there are a lot of free softwares that are created in universities. But a very useful tool is ImageJ, which is free and has a lot of image processing functions in there and so on. All these available programs provide many powerful functions, but none of them can search our ICDD PDF database. So here's where our SAED extension comes in. What goals do we want to pursue with this extension? First of all, it should be regarded as a convenience tool that can be used in the absence of more powerful software. If you have any of the others, you may not need to use this tool. This tool provides simple kinematical SAED simulations, simple synchronized structure viewing, simple image processing, and grid indexing of SAED images, and of course, the only feature that the other programs don't have, a PDF search for 2D cells. A quick word for the different types of SAED images. So here we have an example where we have a standard SAED image, label A, then a so-called precession electron diffraction, PED pattern in the middle, and a kinematical simulation on the right. So when we do kinematical simulations, we have a wide range of different intensities from weak to strong, and we can also, of course, see the reflection extinctions specific to each space group directly in the simulations. And when we have a PED pattern, we can see that this more closely relates or matches a kinematical simulation, because here also we have a wide range of intensities that we can discern, weak to strong peaks, and we can see missing extinct reflections, which is good. So we have a better one-to-one match with our simulation. But in the standard SAED pattern, we may only see a dot pattern like so, where we have a very narrow range of intensity. They all look almost the same intensity, and extinctions may not be apparent or immediately observable because of the dynamic diffraction effects. So there may be dots, spots here visible where actually should be an extinct reflection. It should not be visible. And because of that, we have to include the absences in our calculated or simulated HKL lists so that we can mark the absences. So let's go to a feature overview before we go to the live demo. So first of course, we have the different pattern simulation types. So we have the full 3D reciprocal lattice simulation with the full 3D HKL set that we have simulated. Then we have the SAED layer mode, which is basically just using the same 3D set, but we just cut through the screen plane and only show the zeroth layer. So we always internally, this full 3D set is being manipulated and rotated and whatever. But what is shown on the screen is just a section or a different projection of this full set. So then we also have a lower transmission mode, a lower back reflection mode, and of course the already shown K-pattern mode, which is only available in the EBSD extension. So the simulations are all done kinematically. We can assign X-ray or electron scattering factors. For example, if we were mostly interested in lower transmission or lower back reflection, or we would consider the SAED layer a X-ray precession image, then we could choose the X-ray scattering factors. But for SAED, of course, we would probably choose the electron scattering factors. And the simulation creates HKL lists, which we can then plot with or without the absences. The stereographic projection gives us a quick overview over the symmetry of a crystal. We can easily identify interesting zone axes, directions of interest. And we can show the upper hemisphere of the stereographic projection with the HKL poles, and we can also show the lower hemisphere if so intended. We have a rotatable wolf net. We have clickable poles that give us the HKL indices, and we can also use that context menu to reorient the crystal using the clicked pole indices. And we can also assign traces to the HKL or UVW poles. The internal structure viewer is a relatively simple structure viewer, and the goal here is to minimize any user interactions. So you won't see a lot of GUI elements that let you modify the structure and so on. Most of the interaction with this structure viewer is done by mouse, context mouse and context menus, and you can click the legend, and there's a scroll bar appearing at the bottom with hot zones for things that you can change using the mouse wheel. So now this is a vector graphics viewer. So there are some pros. It uses vector graphics, so it creates scalable, high-quality images. It has an automatic polyhedra generation, and it can export VRML, POV-Ray, animated GIF files. It can also export poster-sized images. And we also provide the option for anaglyph or image pair stereo. The cons are vector graphics, because in this case, we don't have a pixel graphics Z buffer for correctly showing intersecting objects, right? That can only be done in pixel graphics like OpenGL and so on. But the database itself already contains a JMOL viewer, which may give better rendering options for organic molecules and such. Another slight con is that the polyhedra search is limited to tetrahedra, octahedra, and cubes, because this is fully automatic, and we don't want to fiddle around with too many parameters. Other programs may provide many more options to create different polyhedra. And we have, of course, different rendering modes. We can also switch, for example, to a normal 2D drawing, since this is all vector graphics. For image processing, we provide several functions. When we load an SAED image, we can apply a variety of pseudo-color gradients. in order to make it more appealing, instead of using just a grayscale image or whatever the image may be. We have histogram functions that we can apply to change contrast and so on. We have simple exposure adjustments for brightness, contrast, and gamma correction. Or you can use any kind of transfer curves using a spline curve, where you can insert and spline points and move them any way you wish. Other image processing options include the possibility to rotate and shift an image and to change its opacity, which is useful if you have multiple images in your SAED project and you want to see them at the same time. So you will make the images that are drawn later or on top on different layers, you will make them somehow translucent, so you can see all images at the same time. Using the ruler, we can also extract scanline plots from an image, which are shown in the plot window. And we can also embed scale bars for the image, which however requires a camera calibration first. So the camera calibration, the purpose of that is to scale our simulated pattern to the pixel coordinates in the SAED image, so that we can then perform a grid indexing or PDF search. Right. We have two different approaches in the database. The internal SAED module that I have briefly shown uses this setup. It only requires the wavelength or voltage and the camera length or camera constant. In the SAED extension, we have a slightly different approach, since this was derived from the XRD area detector tool in MDI Taos. And here we additionally also require a pixel size. So we have the wavelength or voltage that can be entered, the camera length, and the pixel size of the detector. When they are not millimeters, one just has to make sure that they are the same unit, that the camera length that's being used and the pixel size are of the same unit, so that we can do the angular calibration correctly. So now let's go to the live demo. I will be using an image that I found on the internet. It looks like this. And most importantly, it had some instrument data. It says that the camera length is 600 millimeters and that a 200 kilovolt voltage was used. It also says that this image came from lanthanum cobalt oxide, which may not be true, because this relates to this paper here where the system was studied, lanthanum manganese cobalt oxide. And this paper says that there is a orthorhombic phase, which is manganese dominant, and a rhombohedral phase, which is cobalt dominant. Since this image cannot be indexed fully with a rhombohedral phase, so this seems to be at least a manganese dominant phase. So it should probably be called lanthanum manganese oxide. Okay, let's take a look at the card. This is the lanthanum manganese oxide card, and let's launch, and it has a space group, orthorhombic space group PBNM 62, and we will launch the SAED extension. Let me reset all panels. Let me change the color of these dots proportional to F square, and also the radii proportional to F square. Each viewer, the pattern viewer, and the WolfNet has a scroll bar at the bottom with hot zones where we can use the mouse wheel to change the spot radii, a despacing threshold, intensity threshold, or a label threshold, the intensity threshold for labels. And also some common orientations that we might want to look at. So the same we have in the pattern display. We can also look at the structure at the same time. Let's stay here on this first. So again, we have the pattern display. We are on the layer mode at the moment. So if you want to see the reciprocal lattice, we could switch to this, to the 3D reciprocal lattice. We could say, okay, show this in white on black. So we have the 3D HKL set. Show the layer mode. Show a lower transmission mode. Or a lower back reflection mode. So, but we will stay with the SAED mode for now. So the simulation itself has a choice of background colors, either the default background, a white background, a black background, or no background. When there's no background, you can see these horizontal lines. They are part of the GUI background. We can switch this to a solid background if you don't wish to see them. But it's just to indicate that you're currently transparent. So the SAED project on the left side lists all currently included items, be it images or structure phases. And each of these items has a opacity setting that can be changed. So when we are in the diffraction mode, let's go to a default background. And what we have here is, in terms of mouse interactions, what we do at MDI and all our softwares is very often other programs don't have an easy way to rotate around the screen normal, right? So of course one can use buttons to specify a certain angle and then use buttons to rotate by a certain angle. You can, these buttons, by the way, you can left and right click to reverse the direction. You can also just use the mouse wheel directly on those buttons. The advantage of those buttons are that they indicate immediately the direction in which the rotation will occur. But in general, in a mouse-driven user interface, it's more elegant to do this directly in the plot. So what we do in our software is whenever we right mouse button drag on the right side of either the pattern display or the structure display, we perform a zoom. The same is holds true for a mouse wheel on the right side of the display. When we do a right mouse button drag on the left side of the display, we perform a rotation around the screen normal. And that is sometimes very frustrating in other programs to get this done. So anyway, these are the conventions here. By the way, what I have done with the structure viewer here, by default, only one unit cell was shown. One can look at the shortcuts for the different viewers, for the pattern viewer. So you can use ABC, A, B, C, and D to orient along the main axes. And for the structure viewer, the same. And for the structure viewer, you can also use the key shortcuts 1, 2, 3, 4, or 5 for manually specifying how many unit cells you wish to see. And also one of the shortcuts is Q in order to find polyhedra automatically. If you remember that, you can just press the Q key to find the polyhedra. But there are also shortcuts provided here. For example, here in the atom tabs where we see either the asymmetric unit cell atoms or the full unit cell atoms. When you right mouse click the tab stop, it also performs the search for the polyhedra. The same thing when you just toggle between the structure and the WolfNet, you can right mouse click that same button to find the polyhedra. And the structure menu itself also has an option to find the polyhedra. So this can be done in multiple ways. By the way, when you wish to desynchronize the structure display, you can use this link button on top. Click it to uncheck it, and then you can rotate the structure freely, and it's no longer synchronized with the pattern display. You can resynchronize it using the context menu and click synchronize, or just click the button at the top again, and then the structure display is synchronized with the pattern display again. So let's see. The reflection list, as before, we can either show all HKLs. So in this case, 4,700 HKLs were generated from these options here. On the detector tab, we see the current camera setup. If previous setups are saved, we can also recall them. Let's see. Yeah, these camera settings are only used when we use an image. When we only use simulations, we actually don't need the camera setup. With the simulation, here we select between X-ray and electron scattering factors, and the minimum d-spacing that will be used as a threshold. And we can limit the set of HKLs to 20,000. There's also a checkbox saying skip all and HKLs spots with intensity less than 1%. This is just to keep the 3D set manageable so that they are still being drawn relatively fast. So this is a simulation for a single phase, as you can see. Let's duplicate this structure phase. When you have multiple, you can also switch to a normal display instead of a thumbnail display. Now we have multiple displays. So each of these items in the project has 3 selection states, right? It can be unselected. You can also just use the space bar to unselect an item. When it has a yellow frame around it, it's selected and included in the project. So it's being drawn. The draw order is from the top to the bottom. Unselected items will not be drawn. And the third state is locked. So when it has a red border around it, it's locked. So you cannot use them. You can still click at spots to get information about the spots, but you cannot rotate anymore. And let's include the other. Let's switch to a uniform color, a uniform radii. And let's synchronize across all uniform colors and unify zoom and radii. So now we have 3 patterns being shown here. So the bottom one is selected, and I could rotate it. And I could select the middle item and rotate that. So you can see, you can overlay multiple simulations in the pattern display and also in the WolfNet display. So this would be a multi-phase simulation, right? And instead of just duplicating a phase, you could also add another structure file, CIF or CSF, or add another PDF number to import that. It will be part of the project. The project itself can be saved. Those are simple XML files that have the extension ed.xml. The images and structural data are not included in the project file. Only the PDF number for the structure phases and the file names for the image files will be included there. So don't move the images around if you create project files that you wish to reload. So let me delete these. Okay, so let's stop with this and let's start using images. So let's include an image. So let's add an image to this. So here, this is the downloaded image. So I will disable the structure phase, so I can focus more on the SAED image. So first we want to specify the film center, detect image center. So you can do this with this option, left mouse button, in which case you can drag it around anywhere you wish. But then you have to remember to uncheck it. So I usually do it a different way. I just select this spot that I want to use as the image center. And I right mouse click it to bring up the context menu. And then I say set this point as the center, right? So then we can rotate the image, reset. And on the right side, there are also other options for opacity, more manual rotation options, and all kind of other things that can be changed here. We have the option to apply pseudo-color gradients. So not only do you have these gradients, you can also reverse them. So the top item here is reverse gradient. So in which case, instead of using the colors from left to right, the colors from right to left will be used for the same gradient. We can just invert an image. We have multiple histogram options and symbol brightness or contrast or gamma correction options. Or we have the level tool where we see the histogram levels and we can modify them like so, like in many other image processing programs. Or we can apply a spline curve transfer curve that we can specify. So you left mouse click to insert spline points and right mouse click to remove spline points. So I will just leave the image as is. And I will hide the center. I will select the structure phase. Let me change its color to something that's perhaps a little more visible. And what I want to do is, if the camera constants are not known, so from the downloaded image, they have told us that the camera distance or the camera length is 600, and the voltage was 200, which will be converted automatically to the wavelength. And we don't know what the pixel size is, or the effective pixel size, because this image is probably not the original resolution, which is probably 2048 by 2048. This is a download JPEG images with different dimensions, so we don't know what the effective pixel size would be. So what we can do is, I will just use this structure phase, since I know that is this phase, and I will use it as a reference material to calibrate. So from the pattern, I can see that is probably along one of the major axes, A, B, or C. This pattern seems to match pretty well the B axis. So once I do this, and I can use this as a reference material for calibration. The zoom, by the way, when you use the mouse wheel, you can fine-tune that when you press the control key and use the mouse wheel, then finer steps will be used for the zoom adjustment. The same for the rotation. Usually when the mouse wheel will rotate by 1 degree, with the shift key, it will rotate by 10 degrees at a time. And with the control key and mouse wheel, it will rotate by 0.1 degree. So we use this for multiple functions. Control or shift or alt key, control key will be used for fine tuning, and the shift key for larger steps. Whereas without any of these keys, the mouse wheel will use the default steps by 1 degree, for example. So now here, if I make the simulated pattern match the image, I have inserted the proper wavelength and the given camera length. I touched the camera control. That's why the zoom reset. Okay, now I can also switch to rings, so I can see the pattern better and see how the rings envelop the image that we have loaded. And then I can go to the menu and say calibrate the detector pixel size, the apparent or effective pixel size. So now we have obtained a value here that we now can use. And now we should be ready to also use the measurement tools. For example, let me disable the structure. Let's go to the image. Let's include a scale bar. That should be correct now. And let's include the the ruler. So the ruler is a multi-functional tool. As you have seen, it can open. So you can align this anywhere in the image. You can use the mouse wheel directly to change the number of divisions. You can see the total length, or click here to see the interval length. You can use the mouse wheel also to change the transparency. It has a context menu. You can open it up as a protractor. You can put the lines on, the grid lines. So it either acts as a ruler, like so. When you open it up, it acts as a protractor. By the way, the lower arm, the upper arm, you can move around to change the opening angle. The upper arm will, the lower arm will not change the opening angle. It helps you move around the ruler. You can also grab the pivot point to move the whole tool around. And so basically, we can extract scan line plots that you can see here at the bottom just by moving this ruler around. Let's try to create a grid. So let's open this up. Let's position this somewhere here as the pivot point, the first spot. Let's select the lower arm like so. Let's put the grid on with the mouse wheel. Immediately I choose the number of divisions. Now the upper arm, I will select a point and the mouse wheel select the number of divisions. So now we'll get a primitive 2D cell. I can also switch to transparent, where I can just see this nice grid pattern overlaid over the image. So once we have a grid created like so, and the calibration was done, then we should be able to perform a grid indexing. We have to select one of the structure phases, because there may be multiple structure phases here. So we have to select one of them. That should be so that we know which unit cell to use. Let me change the direction and zoom here, so it doesn't match the image anymore. So by selecting this structure, we have a unit cell that's known now, and now we can right mouse click the grid tool and say index grid, and we have obtained a list of solutions, which is also shown here, from which we then can select a variety of directions. So sometimes you get more, sometimes you get fewer solutions. I would have expected to find fewer. Let me adjust the grid. Usually I only get like 4 solutions instead of such a long list. Let's see if we can get. No, we still get a longer list. But anyway, so this is a list of solutions for the indexing. So, and then you can basically either use the menu and select one of those solutions, and the simulation is overlaid, and the labels will tell you the indices, right? You can change the label color. Let's change the label color to something more visible. And you can apply, of course, the label threshold, so you only label strong reflections instead of, I moved the. With the splitter panel. Another thing you can do is once you have this overlaid, let me disable the labels. We can show the absences also. Let's do the colors again with the normal dots, not the rings. We can also click these dots directly for other measurements. When we use the Shift, Control, or Alt key, just press any of them. I always use the Alt key. I can now click any of these points here in order to show some vectors in the image, which show the distances and angles between those vectors, right? So this these vectors usually will stay there. Even if you zoom up and down a little, they will disappear the moment you rotate the crystal. As soon as one of these reflections disappears, either due to a rotation or other, they will be cleared and disappear. Okay, so now let's do an example for PDF search. Let me remove the crystal structure phase. So now we have a project with only an image. And so as long as we have a calibration, we will be able to perform a search, right? So let's again enable the grid tool. So now we have no crystal structure phase overlaid. We only have an image and a valid camera calibration. We select a grid again. Let's use the same grid. It has roughly equal length axes for this 2D cell. And now we will right mouse click and say search ICDD PDF database. So this window comes up. Here from the grid, we have two vectors, U and V, and an angle. So they specify our 2D cell and reciprocal space, and some error margin, by default 2%. Now, these U and V vectors are very similar, only different by less than 1% difference. So I will use this button to snap them to the same length, to the same average length. Sometimes this button is enabled where you can snap an angle to well-known angles like 60, 90, 120 degrees, if that is not already given here. Now we go to the periodic table. So here we can either activate as allowed elements, light, common, a pre-selection. You can of course also click them. So the blue ones are allowed elements. They're allowed in the formula, and the green ones are required. So here, since we are looking at lanthanum, manganese, or cobalt oxide, so we could do something like this, but we know that lanthanum has to be and oxygen has to be present. So those two are required, they're green, and manganese and cobalt are optional, are allowed. And we expect a maximum of 4 elements in the formula. I don't have to change this, but it may make the search a little faster. So once I have specified my chemistry filter, I can go to the phase tab. I tell the extension which database subfiles I wish to search for this. And by the way, the first time you do this, a indexing step is applied, so an indexing file will be created, which takes about 30 seconds. So this contains unit cell information for the cards in the database so that the search can be performed faster. So once we have the 2D cell from the grid, a chemistry filter, and the subfile selection, we can just click the find button. And we will get a list of candidates here. We can sort them by space group, for example. The list contains also the lattice constants and the assigned HGLs for the U and V vector and the determined zone axis, UVW, and then some residual values. So ideally, the FOM should be sufficient to find the best ones, but because the image can be distorted and the grid may not be give the perfect dimensions of the cell, we cannot 100% rely on the FOM. Also, not the same number of spots may be indexed with those solutions. So is a good indicator, the FOM, but basically we have found our candidates. I usually sort by space group, and then I look through and I can see the formula. And for example, if we want to see a lanthanum manganese oxide in a rhombohedral, so just like we had before, we can look for the rhombohedral like this one, PBMN, lanthanum manganese oxide. This is one option. Let's mark this with a checkbox, and I can see the solution for that card in terms of a zone axis found and HKLs assigned to the U and V vector. And I can say add that phase to the project. So now I have added this phase to the project here. So we have a structure phase. And now I can use the grid while it's still open and say index grid. So now it has used this structure file that we have just found and has used it for indexing the image, right? So we can see the orthorhombic structure, lanthanum manganese oxide, fits indexes into all spots in the image, right? So if we were to consider a lanthanum cobalt oxide, like the original description of the image said, that was a rhombohedral cell, lanthanum cobalt oxide. Let's just use the first one here that appears here. And let's say add this one also to the, then I will disable the manganese oxide and only use this one. So now we have lanthanum cobalt oxide, a rhombohedral in hexagonal setting. And let's see if we can index this. So here we also find solutions, a longer set of solutions. But I think when we go through these solutions, there are always some spots that are not indexed. And that's what made me believe that this image is indeed from a rhombohedral phase, more specifically from the lanthanum manganese phase instead of the lanthanum cobalt phase. If we look at these structures, so they look pretty similar, even though one is orthorhombic, the other one is rhombohedral. So here, if I expand to 4x4x4 unit cells, and I just look at the arrangement of octahedra like so, it looks like so. And if we go to the other one and we expand to 4x4x4 unit cells, for example, we see it is a similar arrangement of octahedra in the structure. So even though this is orthorhombic, the other one was rhombohedral. So, and by the way, if you have noticed that whenever we have selected a structure phase on the left side, we have different set of menus at the top. So for the structure phase, we see the structure menu, pattern menu, stereogram menu, orientation menu, indexation menu. When an image is selected, we see different menus. We see the image menu, the film center menu, and the profile menu. So with this, I think I have shown all the features that I wanted to show. And by the way, yeah, when you change the units, so at the moment the scale the ruler can have different units. So let me reset the colors. Okay, maybe white numbers. Come on. So here, this one shows inverse angstrom. This one shows inverse nanometers. So I can use the mouse wheel on the scale bar to change its background color. I can also switch from black to white text or make it transparent again. And you can also change the unit. This is all done from the context menu of these tools. And the unit that is used here in the ruler, that is also the unit that's being used when we use the Alt key and we click at the spots, and the distances are shown here. They are using the same unit that is used in the ruler. One thing I want to point out, when we have a certain orientation here, let's just show this as like so, without labels. Oh yeah, because this is a rotatable image still, right? So now sometimes accidentally with the mouse interaction, you might rotate it slightly, even though you didn't want to, right? So that's why it may be a good idea if you want to do this kind of measurements with the Alt key and you click these dots and so on, and you may accidentally rotate it and this will go away. So in order to prevent that, you may want to lock the image. So just click on it. So it has the red border around it and it's locked. And then you can use your, with the Alt key and click these dots. And then there's no danger of accidentally rotating the crystals and the vectors will disappear. And okay, let's also go to the theme. So for the GUI theme, you can switch between light themes and dark themes. And all this information is usually saved whenever you save a project file, which you can then later recall from the recent menu or from the open menu. This information is part of the project file. So that sometimes it may come up with a light GUI and sometimes may come up with a dark GUI. That depends on what settings were saved in the project file. Okay, I have shown all the features that I wanted to show. And with this, I conclude this presentation. If you have interest in the product, you can contact us by email at sales@icdd.com for product info, price quotes. And if you want interested in tech support or you want to submit sample files or images, you can contact us directly at support@materialsdata.com.